We started the class by talking about classical astronomy. We moved on to slowly expanding our point of view on the universe, starting with the solar system, proceeding to stars and then star clusters and galaxies last week. And it seems only fitting to end our journey by talking about the whole shebang, seeing what it is that we can say about the universe as a whole. And the principle that guides us in being able to say anything at all about the universe is the cosmological principle, the assertion that the universe is homogeneous and isotropic. Homogeneous, recall, means that there are no preferred locations in the universe. Everywhere is the same as everywhere else. In particular, this implies there's no point that is the center of the universe, nor is there an edge to the universe. Those would be distinguished points, and there are none. Furthermore, the universe is isotropic. It's the same in all directions. It's the same in all directions, no matter where you are looking from. And so the existence of a homogeneous isotropic universe, all of this symmetry, is what's going to allow us to say something useful about the universe. Now, clearly, the universe is neither homogeneous nor isotropic at small distances, so the best we can hope to imagine is that, in fact, at large distances, when you average out little perturbations like stars and galaxies and clusters and superclusters, at really large distances, there is no leftover structure, and we saw some evidence for that last week in the decrease of the correlation function in galaxy counts at distances of order 100 megaparsec or more. We will see a lot more evidence this week, and I want to say that we already saw another indirect piece of evidence, which is the Hubble flow that we discussed last week. So at the end of last week, we mentioned Hubble's result that galaxies are receding from us, and the average recessional velocity is proportional to the distance of galaxies, the constant of proportionality being the Hubble constant. And so here's a cartoon of what that could look like. Here's a one-dimensional universe. Of course, I've only drawn a piece of it. These arrows are meant to indicate that the universe goes on in all directions. This is the universe at, say, t equals 0. There are 3 galaxies here. These are the same 3 galaxies over here at some later time t. And we can label them. We'll label this galaxy number 1, 0, 1, minus 1. And if I wasn't so stingy, I would have added galaxy number 2 over here and galaxy number minus 2 over here. And what we see is that the farther a galaxy is from galaxy 0, the faster its motion. The velocities of these galaxies are attempting to represent the Hubble law. And in particular, I'm going to erase all my figures when I move on. But here we go. If I label these galaxies I, so I counts the name, is the name of a galaxy, and the position of a galaxy at time t is its position at time 0 times 1 plus h0t. This, if you look at the speed that this, or the velocity that this position implies, then this is just a constant shift. This is xi of 0 plus xi of 0 times h0t, and that tells you that the velocity of the ith galaxy is just h0 times xi of 0. The farther a galaxy is, the faster it's moving. This is the Hubble expansion law, and this is all from the point of view of galaxy number 0. In particular, xi is the distance of the ith galaxy from galaxy number 0. Vi is the velocity as drawn in this graph relative to galaxy number 0. What if you try to represent the same thing, but from the point of view of galaxy number 2? Well, in that case, what goes on, of course, is that the velocity you measure, if you said j equal to 2 here, the relative velocity, this is all non-relativistic, of galaxy I is the difference in velocity between I and j. Plugging the values from the Hubble law in, I see that indeed this is the Hubble constant times the relative position of galaxy I relative to galaxy j. In other words, Hubble's law looks the same as observed from galaxy j as it did observed from galaxy 0. Now let me erase all my scribbling so we can see what we're doing and make a point. This is true for Hubble's law because it is a linear dependence of velocity on distance. Imagine, for example, that Hubble had discovered a quadratic dependence of velocity on distance. In other words, galaxies twice as far would be moving 4 times as fast rather than twice as fast. If this were true, then imagine that that's fine. Each of these galaxies is moving with a velocity proportional to the square of its distance. However, if you now observe the relative velocity of the ith galaxy relative to the j, so if you're now observing with from the point of view of galaxy j, then the relative velocity is the difference of their velocities, and that is not the same as the quadratic velocity law you would have obtained by simply imagining that this law, just as it applies viewed from galaxy 0 applies viewed from galaxy j. In other words, a quadratic velocity law would not be consistent with the homogeneous and isotropic universe, but the Hubble flow is. So the Hubble flow is another subtle hint about that we may consider the universe isotropic and homogeneous. We'll get many more of those, but for now we're just going to assert it. Now the Hubble flow tells us a few other things that I want to emphasize. One is, at every location, at every event, at every location at any given time in the universe, the Hubble flow selects, in fact, a preferred rest frame. The reason is that this is the frame in which the Hubble flow looks isotropic. Of course, if I see an isotropic Hubble flow, and you are moving relative to me and at my same position at the same time, at the same event, you are moving with some large velocity relative to me, then in the direction of your motion, galaxies will appear to be receding at a smaller velocity than what I observe, whereas behind you, galaxies will be observed to be receding with larger velocities, all this completely non-relativistic, and it is not a violation of special relativity. This is not a preferred reference frame with respect to the laws of physics. It's a preferred reference frame with respect to the positions and the motions of the objects in the universe. And so the observation is that by and large, galaxies follow the Hubble flow. They have peculiar velocities. They move relative to the local Hubble flow. But on average, in any region of space, at a given time, the average peculiar velocities of the galaxies average to 0 if the region of space is large enough. By and large, galaxies follow the Hubble flow, and then relative to that, they have their peculiar velocities. And so at every point in space and time, at every event, there's a unique reference frame in which the Hubble flow looks isotropic. Now, we use the Hubble flow, or we discover the Hubble flow, by measuring the redshift. Again, everything here is non-relativistic. You remember that the redshift z is given by 1 plus z is lambda over lambda 0, and this is equal in turn to 1 plus v over c, and v over c in turn is 1 plus h0 d over c. So the redshift was given by h0 over c times d, so we have a linear redshift distance relationship. When is this valid? Well, this is valid because we used a non-relativistic version of the Doppler formula. We expect it to be valid for small non-relativistic velocities, and this corresponds to distances small compared to c times the inverse of the Hubble constant. In other words, there's this distance, a typical size, characteristic size of the universe that is, and the Hubble law we expect and we found holds for distances small relative to this. What happens if you want to understand larger z's? Well, you could try to use the special relativistic Doppler law formula, replacing this by that square root. As we saw in the homework, that doesn't quite work. And in fact, in the context of a dynamical, expanding universe, corrections to this beyond small z are going to be sensitive, on the one hand, to relativistic corrections, because the velocities that you observe when z is not much less than 1 are going to be relativistic. On the other hand, the light will have been traveling a significant fraction at z not much smaller than 1 of the history of the universe, and so you will be sensitive not only to the state of the universe now, but to the entire history of the universe. And in particular, if you try to extend an expression like this to distances d that are not small, relative to the amount of the distance that light would have traveled in the age of the universe, then when you're talking about objects that are that far away, the definition of distance becomes ambiguous. What do you mean by distance? You can't go around laying a ruler from one galaxy on one side of the universe to a galaxy on the other side of the universe, because if those galaxies are moving, then by the time you finish laying your ruler, they will not be where they were when you started. So even understanding what we mean by distance will become ambiguous, and because of all of these, we would be very surprised to find that the special relativistic expression for Doppler shift inserted into this would give an actual correct interpretation, and understanding the redshift distance relation will tell us, in fact, a lot about what goes on in the universe. Now, naively, just extending from this the statement that distances between galaxies at time t are given in terms of their distances at time 0 times 1 plus h0t, then it's clear that going into the past things were closer, and you predict that when t is equal to the inverse Hubble constant, distances were all zero, so you predict a singularity or a Big Bang with a characteristic time of 13.8 billion years, given by the inverse of the Hubble constant. Now, this assumes some sort of constant ongoing expansion extrapolated into the past. We don't really expect that. Hubble certainly knew not to expect that. What are we describing? We're describing a bunch of massive objects, galaxies, flying away from each other. These objects interact principally gravitationally, and what we expect is gravitation is a long-range force. These galaxies are distant, but there's a lot of them, and we expect that these galaxies flying apart will be slowed down by gravitational interactions. Sure, I can make something fly away from a massive object by giving it the correct initial conditions, like I can throw a rubber ball in the air, but eventually gravity will slow it down, and the question is, if I throw it fast enough, it has the escape velocity, it'll slow down but keep receding. If I throw it with less than the escape velocity, it'll slow down, stop, and return. But Hubble certainly did not expect his law to extend to the entire history of the universe, because what one expects is that expansion is slowing down. This is a very reasonable expectation, given our understanding of gravity. Now, just this bit of the picture, as a first tidbit from this week, is going to give us the resolution to Olber's paradox that has followed us for a few weeks. And the resolution is precisely the one that Edgar Allan Poe intuited so many years ago. In a universe whose age is finite, the sky is dark even if the universe is infinite, and even if it's filled with a homogeneous distribution of stars. There are stars that are so far away that light from them has not yet had time to reach us, and in fact, if the universe is infinite, almost all of it is too far away for us to have seen yet. In fact, we only see a finite distance out into the universe because light has only had a finite amount of time to travel from there to here. This means that most of the infinite sum of equal terms that made the divergence that caused the paradox in Olbers, most of that infinite sum is not yet visible, and so at any given time you see out to a finite distance. Within a finite distance, the stars take up a small fraction of the sky, and the sky appears dark. Of course, we expect by now that it's not that you see all the stars up to a certain distance, and then beyond that it's dark. That kind of sudden transition is not what happens. Stars closer and closer to the maximal distance will be increasingly redshifted so that they will be dimmed, and eventually there'll be sort of an infinite dimming, and we will not see any stars past a particular distance. We'll talk about that. We haven't seen the entire universe yet. As we'll see by the end of this week, we never will, in fact. We've seen most of what we ever will see, and understanding the meaning of that statement will be part of the joys of studying cosmology this week. And so what is it that we're going to do? Well, we're going to look at what we can say about the physics of a universe that is homogeneous and isotropic, but not time-independent, is changing with time, expanding or possibly contracting. We're going to learn how to extend those ideas to a relativistic theory, because by the time you reach deep into the past of the universe, the recessional velocities of objects become relativistic, and clearly the framework for discussing gravitation at those distances is going to be Einstein's general relativity. We'll learn how that simplifies in the context of a homogeneous isotropic universe and what that predicts about the evolution of the universe. And then we'll talk about, well, what are the parameters of the model we have of the universe? What is it that we have learned about the makeup of our universe, how we have figured it out, and what this tells us about the future, what this tells us about the past, and setting us up for even more detailed discussion next week of details of the distant past and what really happened in the early universe, who it was, and how that this threw this rubber ball into the air that began this cosmic expansion, of which we are now seeing the late stages. And to spoil the surprise, here is the result of what we know about our universe. Our universe, the total energy density in our universe, is made up in the following way. About 5% of it is made up of atoms, by which I mean protons, because most of the atoms in the universe are hydrogen atoms. And so about 5% of the total energy density of the universe is in the form of matter as we know it, mostly hydrogen. About a quarter of the mass is in helium, and trace amounts of all the rest of the stuff we're made of. About 24% is dark matter, those WIMPs, about whose properties we have some conjectures, but which we have never detected. And then the remaining about 71% of the energy density in the universe is something we call dark energy, by which we mean we have no idea, really, what it is that causes it or what it is that it represents. We will talk about what it is we know about this thing, how we know it is not the same as, say, a type of dark matter. It is indeed something qualitatively different. And next week, we will talk about some ideas that might actually implement a physical model for what dark energy could possibly be. Should be an exciting week.